Hello viewers, today in this part of the lecture we will be discussing logic gates and Boolean algebra. The brief outline for today's discussion will be, we will first start the discussion of logic gate and what is a logic gate. Then we will discuss various types of logic gates, and there are three category of logic gates which we will discuss in today's lecture. So, the first category is basic gates, which includes NOT gate, AND gate and OR gate. Then the next category of gates will be universal gates, which includes NAND gate and NOR gate. And finally, we will have arithmetic gates, which includes XOR gate and XNOR gate. Then we will discuss how universality of gate can be proven and what is the benefit of using universal gate in logic circuits. Then we will discuss three important theorem, and that is Boolean theorem, which constitutes of more than one theorem. Then we will discuss De Morgan's theorem, and finally, we will discuss principle of duality. Logic gates. So, logic gates are the basic components of digital circuit. It performs logical operation on one or more logical inputs and produces only a single logical output. And as we discussed in the outline, that there are three categories of logic gates. The first one is basic gates, which includes OR, AND and NOT gate. So, these are the basic gates which will give us higher and complex logical circuits. Then the second category is called universal gate, and it includes two types of gates, that is NOR gate and NAND gate. So, we will show that the NOR gate and NAND gate is sufficient to get any type of gate that can be part of any category of gate that we have mentioned. And then finally, we will have the gates which are called arithmetic gate, and they are named as XOR gate or XOR gate and XNOR gates. So, let us first discuss the very basic gates, and the first very basic gate that we want to discuss is NOT gate. And the symbol of NOT gate is shown in this slide, where there is an input and we obtain an output from the gates, and this output is the complement of the input that we give to the gate. Now, here as you can see, the input is named as A and the output is named as X. Now, if we look at the truth table for the NOT gate, then we will see that for an input of 0 at the input point A, we get an output of 1 at the output point X. Similarly, if we give an input of 1, then we obtain an output of 0. So, from this we can say that for a high input, the output will be low and vice versa. As I said, the output here is shown as X, and that can be written as A bar, because the bar represents the complement of the input A. The next basic gate that we want to discuss is AND gate. Now, in AND gate, the output is high when all the inputs are high. Now, in this slide we have shown the symbol of AND gate, which has 2 inputs and 1 output. Now, it is not necessarily important to have only 2 inputs from the AND gate. You can have more than 2 inputs from the AND gate, but the output is always 1. So, the truth table for AND gate is shown in this slide. Here for 2 input AND gate, we have 2 inputs A and B and an output that is represented by X. Now, as you can see, the output is 0 whenever the inputs are either both of them are 0 or one of them is 0, but the output will be 1 when both of the inputs are 1. Now, we can mathematically write an expression for the AND gate. To represent the output of the AND gate, we can write the following equation, and that is the output X is equal to A dot B, where dot is the AND operator. Now, there are particular features which AND gate needs to satisfy, and the first feature is it obeys associative law. And what is associative law? Now, if we take the input A and apply the AND operator on the 2 other inputs B and C in the following way, that is A dot within bracket B dot C, then it must be equal to within bracket A dot B dot C. So, in this way we can say that AND gate obeys associative law. Similarly, AND gate also obeys commutative law, and what is that? It means A dot B is equal to B dot A. Now, we can prove both the laws for AND gate by using the truth table, which is very easy to prove. Now, from the truth table of 2 input AND gate, one can show that the enable and disable function. Here, as you can see in the truth table shown in this slide, the upper 2 input conditions give rise to the output as 0, and these 2 input conditions are called disable conditions, and the lower 2 input conditions, in one case it gives 0 and in the other case it gives 1. That means, the inputs decide the output from the AND gate, and that is why these 2 conditions are the enabled condition. Now, the next basic gate that we want to discuss is OR gate, and in OR gate the output is high when any one or both the inputs are high. And here in this slide we have shown the symbol of OR gate, which has 2 inputs A and B and one output which is X. So, OR gate also does not necessarily have 2 inputs, it can have more than 2 inputs, and the truth table for the 2 input AND gate is given in the slide, where the 2 inputs A and B gives rise to a higher output across X when either one of the inputs are high or both the inputs are high. Now, mathematically we can represent the output from the OR gate in the following way, that is X is equal to A plus B, where plus is OR operator. So, OR gate, like AND gate, also obeys associative law and commutative law, and that is A plus within bracket B plus C is equal to within bracket A plus B bracket ends plus C, which defines the associative law, and the commutative law can be represented as A plus B is equal to B plus A. And here also both the laws can be verified by using truth table, and For a 2 input truth table, the first two conditions give rise to enable condition and the last two conditions give rise to disable condition. Now, we will discuss the universal gates, that is NAND gate and NOR gate, and the first universal gate that we want to discuss is NAND gate. The operation of NAND gate is same as AND gate, except that the output is inverted. That means, the output that we obtain in NAND gate is complement of the output that we obtain from AND gate, and the symbol for NAND gate is the following given in the slide, where we have shown a 2 input NAND gate. The input A and input B gives rise to an output X, and mathematically we can write the output X is equal to A dot B bar, and this bar represents the complementary output that we obtain if we compare with the AND gate output. Now, the truth table for NAND gate operation is also shown in this particular slide, where if we observe the output from the column in the truth table, then it is exactly opposite to the output that we obtain from an AND gate. And we can always make an AND gate by using an OR gate, and that gives rise to bubbled OR gate. And NAND gate, unlike, only obeys commutative law, but it does not obey associative law. Now, the next universal gate that we want to discuss is NOR gate, and the operation of NOR gate is same as OR gate, except the output is inverted. So, if we compare the output of NOR gate to that of OR gate, then we will find that the output that we obtain from NOR gate is complementary to the output that one can obtain from OR gate, and the symbol of NOR gate having 2 input and 1 output is shown in this slide. Here the symbol is close to an OR gate symbol, except there is a bubble just before the output from the gate. And the truth table for the NOR gate is also shown in this slide, where if we observe the output from the NOR gate, then if we compare it with the OR gate output, then it is complementary to the OR gate output. So, this NOR gate is also called as bubbled AND gate, because we can create the NOR gate by using an AND gate and the bubble which represents the NOT gate applications. This gate also obeys only commutative law, but it does not obey associative law. Now, because we categorize the NAND gate and NOR gate into universal gate category, then how to prove that both NAND gate and OR gate actually gives us the universality factor. So, this universality is coming into picture because we can construct each and every gate that we are discussing in this lecture from either NAND gate or NOR gate. So, first let us see the use of NAND gate to construct all the gates that we will discuss in today's lecture. Let us first construct NOT gate from NAND gate, and this can be obtained by using only one NAND gate, where the inputs, if we consider a 2 input NAND gate, then both the inputs need to be same, that is the input A is given across the two inputs, and hence we get an output that is equal to A bar. And as we know that A bar is the complementary of the input A, which is the output that one can obtain if we provide an input across a NOT gate. Similarly, we can construct a AND gate from a NAND gate. So, we need to have two NAND gates in which the first NAND gate will be connected to two inputs, and the output that is obtained from the NAND gate is fed into the two inputs of the second NAND gate, and the final output is similar to the output that is obtained across the AND gate, and hence in this way we can construct NOT gate and AND gate by using NAND gate. Similarly, we can construct OR gate by using 3 NAND gate, and here as you can see we have used 3 NAND gate to construct an OR gate, where the first 2 NAND gates are having 2 inputs which are common, and the output from these 2 NAND gates are going to the third NAND gate, and the output of the third NAND gate is same as the output that one can obtain from OR gate. Similarly, we can construct the NOR gate by using NAND gate, and that is by using 4 NAND gate, in which the first 2 NAND gates output is connected to the third NAND gate, and the output from the third NAND gate is connected to the fourth NAND gate, and hence the output or the final output that we obtain from this logic circuit is same as the output that one can obtain from NOR gate. And similarly, we can construct XOR gate and XNOR gates by using NAND gate, and this is shown in this slide, where you can see the 4 NAND gates are connected in such a way that the output that is obtained is equivalent to the output one can expect from XOR gate, and similarly the 5 NAND gates are connected in such a way that the output, the final output one can obtain is same as the output one can find out from XNOR gate. And in this way we can say that NAND gate can be used for the formation of any type of gate that we have mentioned so far. Similarly, we can use NOR gate to construct any type of gate that we have mentioned so far. So, let us see how we can construct all these gates. So, the NOT gate can be constructed from NOR gate by using only one NOR gate, in which both the inputs are of same value, that is the input is A and the output is A bar, which is the output that is obtained from a NOT gate. Now, the next thing that we want to show is AND gate from NOR gate, and for that we have used 3 NOR gates, and the final output that is obtained from one of the NOR gates is similar to the output that one can obtain from AND gate. Now, we can construct the NAND gate and OR gate by using NOR gate, and for NAND gate we need 4 NOR gates, and these 4 NOR gates are arranged in the way that is shown in the slide, and the output that is obtained from this logic circuit is same as the output that one can obtain from NAND gate. And similarly, one can obtain OR gate by using only 2 NOR gates, and the output from the final NOR gate is same as the output that one can obtain from OR gate. In the same way, one can also show that the output of XOR gate by using NOR gate, and for that we use 5 NOR gates in such a way that the final output that one can obtain from this combination of NOR gates is same as the output of an XOR gate, and for XNOR gate we have used 3 NOR gates in such a way that the final output of this logic circuit gives rise to or is equal to the output that is obtained from XNOR gate. So, in this way we can also show that the NOR gate is one of the universal gates, and all these gates output can be tested by using the truth table, and hence we can say that NAND gate and NOR gate are the universal gates. Next type of gate that we want to discuss is called arithmetic gate, and the first arithmetic gate that we want to discuss is XOR gate. This is also called as exclusive OR gate, and the short form is XOR gate. This gate gives high output when one input or the other input is high, but not both the inputs. If both the inputs are high, then the output will be 0. So, the truth table for this gate is shown in this slide, where the two inputs A and B are giving rise to a higher output when either of the inputs are high, and we can show the symbol of XOR gate in this slide, and how an XOR gate can be constructed by using a combination of NOT gate, AND gate and OR gate, that is also shown in this slide. And mathematically the output from the XOR gate or XOR gate can be written in the following way, that is X is equal to A bar B plus A B bar. The next category or the next type of arithmetic gate that we want to discuss is XNOR gate. The exclusive NOR is the complement of exclusive OR gate, meaning the output that one would obtain from XNOR gate is the inverted of the output that one can obtain from XOR gate. Now, a comparison of both the truth table gives the idea about the operation of XNOR gate. As you can see, we have the truth table for both XNOR gate and XOR gate in this slide. Here the output that is obtained in XOR gate is opposite to the output that is obtained in XNOR gate, and the symbol for XNOR gate is also shown in this slide, and we can construct the XNOR gate by using a group of NOT gate, AND gate and OR gate. So, here we have shown both the logic circuit as well as the logic symbol for the XNOR gate, and here, as unlike the XOR gate, here the output is high when one of the inputs is high. Next we will discuss the Boolean theorem. The Boolean theorem, we have given a flavor of Boolean theorem when we discussed AND gate and OR gate. Here we will discuss in detail how these theorems are useful in different types of logic operation. So, the first theorem is the associative law of addition and multiplication, and when we say addition and multiplication, they explicitly represent the OR and AND operations from the OR and AND gates. So, when we want to show the associative law to be applied, then we can mathematically show that A plus within bracket B plus C bracket closed is equal to within bracket A plus B bracket closed plus C. And for multiplication, we can show the associative law as A dot within bracket B dot C bracket closed is equal to within bracket A dot B bracket closed dot C. Similarly, the commutative law of addition and multiplication can be written in the following way, that is A plus B is equal to B plus A and A dot B is equal to B dot A. And there is another Boolean theorem which is important, is the distributive law, and that is also shown for both addition and multiplication, in which the addition distributive law is as follows, that is A dot within bracket B plus C is equal to A dot B plus A dot C. And in another form we can write within bracket A plus B bracket closed into within bracket C plus D bracket closed is equal to A dot C plus A dot D plus B dot C plus B dot D. And apart from the three theorem that we mentioned, there are also rules which are mentioned in this particular slide, and these rules are also important to simplify the logic circuit that we come across while solving the digital circuit for the digital output that one needs to obtain from a given circuit. The next important thing that we want to discuss is De Morgan's theorem, and the theorems are used to simplify logic circuits involving NAND and NOR gates, and the theorems are stated as follows. The first one is A dot B bar is equal to A bar plus B bar, and the second theorem is A plus B bar is equal to A bar dot B bar, and both the theorems can be proved by using the following truth table. Here we have shown the truth table for both the theorem, in which one of the outputs is A dot B bar and the other output is A bar plus B bar. Here, as you can see from the truth table of both the cases, the outputs are exactly same, and hence we can prove that the first theorem of De Morgan's theorem is proven. And this says that an AND gate with inverted output is equivalent to an OR gate with an inverted output. Similarly, we can prove the second theorem using truth table that we used in the previous theorem of De Morgan's theorem. So, here we can say that an OR gate with an inverted output is equivalent to an inverted input AND gate. And finally, we will discuss principle of duality. It states as follows: the duality property of Boolean algebra states that all the binary expressions remain valid if the following two steps are performed. That is, the first step is interchange AND and OR operators. Then the second step is replace all ones by zeros and all zeros by ones. If both the operations are applied and still the Boolean algebra remains same, then we call it the principle of duality, and we can understand that by the following example. If we have an expression of A plus B is equal to 0, the duality can be obtained by replacing AND operator plus by OR operator dot and 0 by 1. So, the duality of A plus B is equal to 0 is A dot B is equal to 1. So, viewers, today whatever we discussed in the lecture can be summarized by using the following few important points. We started the discussion with the understanding of what is a logic gate. Then we discussed the various types of logic gate, which are categorized into three types. First one is the basic logic gate, which includes AND, OR and NOT gate. Then the second one is the universal logic gate, which includes NAND and NOR gate. We also proved that why NAND and NOR gate are called as universal gate. And finally, we discussed the third category, that is arithmetic gate, which includes XOR and XNOR gate. And then we discussed the three theorem, that is the Boolean theorem, which includes three laws and some rules, and the second one is De Morgan's theorem, which is useful for simplifying logic circuits having NAND and NOR gate. And finally, the principle of duality, which can be valid for with various Boolean algebra by using two steps. So, viewers, whatever we discussed could be very much helpful when one needs to design a digital circuit, and I am hopeful that you would have loved today's discussion. Thank you very much.